All right, Chemistry 3101. We've made it to the last chapter of Organic Chemistry 1, which is the synthesis chapter. And really, this chapter focuses on chapters 7, 8, and 9, and 10. Okay, we really just focus on those four chapters. Will the material from other chapters show up? Sure, yeah, to some extent, but not nearly as much as those chapters. And what's, kind of the main thing that students in Organic Chemistry 1 need to learn about synthesis? The first thing they need to know are one-step syntheses, which is just another way of saying the reactions, right? All the different reactions that we've learned. It says here, and I'm reading right off the slide, it says solving a synthesis problem, providing the reagents, can be straightforward when there's only one reaction required. But obviously, we're going to look at many questions where there are more than one reaction required. So if you had this question here, so this first compound, this alkene, is called isobutylene. If you take isobutylene and you treat that with bromine, right? Everybody here, I'm sure, would nail this, right? And they'd say, well, it's just a bromination. All you have to do is add Br2 to it. There's no stereocenters to worry about. I know that it occurs with anti-addition, but again, this isn't a stereocenter, neither is this, so I don't really have to worry about that. But as you've seen many times in this class, okay, you have to master all of these reactions and the reagents required before you can really get into hardcore, multi-step problems. And is it challenging to do? Of course. Absolutely it is. And so it's a good idea to tackle problems like this one here. Let's check it out. It says, identify the reagents that could be used to accomplish each of the transformations shown here. If you're having trouble, the reagents for these transformations appear in the review of reactions of at the end of chapter 8. So sometimes students will ask me, is there a review, like a comprehensive review? Well, the reviews at the end of the chapters are very comprehensive and very well put together. So if, let's say, you're having problems with the reactions in chapter 8, which is the alkenes chapter, I would go to the review of the reactions at the very end of the chapter, and what you'll find is that all of those reactions that you covered in that chapter will be nicely laid out and summarized for you. All right, but you can see the last thing that it says is you should try to do these without help. Let's say, you start with this first reaction. I don't know, let's start with this one here, okay? Could anybody tell me, I'll just throw that out there to my students, I'm adding bromine to the molecule, and I'm also adding a hydrogen. So this is hydrohalogenation. Could anybody tell me, would this be Markovnikov or anti-Markovnikov, the one that I have in the red circle here? Would that be Markovnikov addition or anti-Markovnikov addition of HBr? Yeah, absolutely. Yes. Yeah. Yeah. All my students are on the right path. Yeah, everybody's got the same answer and everybody's right. Okay, everybody's saying, well, that's anti-Markovnikov addition, right? Because this carbon is the one that's richer in hydrogens, and that's the one that's actually taking the bromine. The other hydrogen is going over here, right, from my HBr. And we discussed this reaction in detail in chapter 8, and we looked at the mechanism in chapter 10. So for this, we would need HBr and an organic peroxide. Okay, well, if that is anti-Markovnikov, so anti-Markovnikov, then it doesn't come as much of a surprise that the next reaction, and I'm going to go clockwise, this one here is a Markovnikov addition of HBr, right? Markovnikov addition. Now, in this case, once we protonate it, right, this is the carbon that's going to take on the hydrogen. There's going to be no carbocation rearrangements. We have the bromide come in as a nucleophile. And so all we would need here is HBr, nothing else, just HBr. So that's Markovnikov addition of HBr. I'm going to throw this out here to my students. For the next one, you see you start with this big old ring, 1-methylcyclohexene, and then you end up with an aldehyde and a ketone. And I know that most of you probably know the answer, but could anybody throw me a reagent that I might use for this? Yep, absolutely. Absolutely. Everybody Edwin, Kelly, Mackenzie, everybody's correct. Okay, you're all correct. You knew right away it's ozone, right? This is ozonolysis. The only thing that I think is tricky about ozonolysis, because students usually do a very good job of remembering the first step, is that we looked at ozonolysis of alkynes too, didn't we? Right? And the second step in the ozonolysis of an alkene is dimethyl sulfide, DMS. Okay? Or you can use zinc and water together. Okay? Now, when we look at alkyne ozonolysis, the second step is just water, isn't it? Right? So I'd say that's the trickiest thing here would be would be that. So this reaction, we call it either oxidative cleavage or we call it ozonolysis, so ozonolysis. And you think about what that means, right? You learn in biology about glycolysis, right? What are you doing? You're breaking apart glucose. So any kind of lysis means you're breaking something apart, and you use ozone to do it. So ozonolysis. All right. The next one is probably the reaction that we had the most conditions for, right? Is this one here. This one here, which is a dihydroxylation, but it's a syn dihydroxylation because both of the hydroxyls are added on the same face of the molecule. So this would be syn dihydroxylation. Okay, we're adding two hydroxyls, and again, they're on the same face of the molecule. Now, the most effective way, I think, to do this would be to use osmium tetroxide, so OSO4, in a catalytic amount. Oops. Okay, catalytic amount, like that, and then NMO, which is N-methylmorpholine N-oxide. We looked at that very quickly in this class, and that is a co-oxidant because I told you that this is really dangerous. So the NMO basically regenerates it. Yes, absolutely. I see that somebody typed it into the chat, right? Faster than I came up with it, right? My students get really fast by the end of the class. Right, and are there other options for this one? Yes, okay. Another classic, if you are the kind of person who likes to Google everything, and I always end up with somebody in the class who's like, I want to Google everything that we do, you know, and double check it. And there's nothing wrong with that at all. I encourage it. But another option that's really popular is to use potassium permanganate in a base like sodium hydroxide at cold temperature. Okay, I'm just going to throw that in there. I don't always do this when I lecture on this, but since in the summer it's probably fresh in your mind. These are good reaction conditions because potassium permanganate is not toxic, so you don't have to stress about it. The problem with these conditions is that potassium permanganate just is such a strong oxidizer. It just oxidizes the heck out of everything. Anyhow, I digress. Let's move on and take a look at the next one, which involves anti-dihydroxylation. So this is I'll just put it like this, anti-dihydroxylation. And this one is a two-step process, isn't it? In the first step, we treat the alkene with a peroxy acid. You could put in MCP, BA, or you could put in RCO3H. Either way, it's a peroxy acid. They both mean the exact same thing. But that forms an epoxide, doesn't it, right? This step, all it does is form this molecule. And of course, I'm going to have to delete this after. But all you make is that epoxide, right? And then in the next step, you blow that epoxide open by treating it with aqueous acid. So two steps. All right. The next one is we're making a halohydrin. So making a halohydrin, let's see here. We've got son of a gun, I didn't mean to do that. Please tell me it didn't delete everything. Okay, there we go. I deleted some of it. Let me spruce it up while you're thinking about the next reaction conditions. If somebody wants to type them in, go for it. NMO, I'll just leave that like this. And then I'll put and then, sorry, the halohydrin formation. So for that, we just used bromine. So just bromine, but now our solvent is water, right? So we form the bromonium ion. Yes, absolutely. My students are 100% correct. I'm looking at the chat. Absolutely. Yes. I'll give that a thumbs up to the person who came up with that. All right, there you go. Awesome. So there we go, bromine and water. So that's halohydrin formation. The next one is just a bromination, which we know occurs with anti-addition. So that is just treating the molecule with bromine. Hey, I have a question. What about the next one? Going from the alkene to the alkane. Could anybody make a suggestion there? From an alkene to an alkane. What do you got? Yes, absolutely. Absolutely. Yep, everybody is correct. Absolutely, 100%. Yep. We're just going to use hydrogen. And if you want to use, some of my students put platinum, so we'll put that. If you wanted to put palladium or nickel, that works fine too. What about the next one? The next one is a cool one, right? This is an anti-Markovnikov addition of water across a double bond. So this is hydroboration oxidation. Let me write down the name. So this is hydroboration. And then the second step is oxidation. And that's a two-step reaction, right? In the first step, we're going to treat the molecule with borane, BH3, and THF. And then in the second step, we treat it with hydrogen peroxide and sodium hydroxide together for the anti-Markovnikov addition. And I want to remind you that this is a syn addition, isn't it? We add the hydroxyl and the proton in the anti-Markovnikov fashion. They both are added to the same face of the molecule. So it's important that you know that not only is it anti-Markovnikov, so we'll put down here anti-Markovnikov, but it's also syn addition, and that is important. All right, the next one is just a Markovnikov addition of water. There are no carbocation rearrangements to stress about here. And so I would just treat that with aqueous acid, right? Just treat that with H3O plus. And there you have it. And then the last one is if we take, oh no, there's a couple more here, aren't there? Okay, well, let's do this one here. We want to do an E2 reaction. We have this type of beta proton here. We have this type of beta proton here. If we wanted to abstract the one in red, we would use a hindered base, right? Like for this one, you'd use potassium T-butoxide to give you the Hoffman product, but that's not what we want to make. If we want to abstract the one in blue, we're going to use a base like sodium methoxide, which is a less hindered base, which will give us the Zaitsev product. Anyhow, I'm going to delete this off of here. And the last reaction is what we covered in chapter 10, isn't it? This isn't even a chapter 8 reaction. This is just halogenation, right? And we talked about this in detail in the last chapter. So for that, you would use bromine, bromine and light, which would generate the most stable radical, and then it does the bromination. And there you have it, okay? And it could be light or it could be heat. Either way is going to work. You know, now that we've gone through all these, I just want to remind you that there's one reaction. I mean, besides this one, where we learned that you could use osmium tetroxide, then sodium bisulfite or sodium sulfite in water. Yes, we did cover that. But there is one reaction that's kind of left out here. And it's the oxymercuration demercuration. So that was the reaction where we did the Markovnikov addition of water to avoid a carbocation rearrangement. So that would technically go here, but you don't need to use it because there's no carbocation rearrangement here. But just to, jog your memory, the conditions are to use mercuric acetate in the first step with water. And then in the second step, we use sodium borohydride. So it's really the only reaction that we looked at in detail that's not covered in these reactions. But again, you could use it for this transformation. It's just that there's no need. Okay, since there's no carbocation rearrangement to worry about. So there you go. That's a pretty good review of chapter 8. If you feel confident, and I'd say at this point, 90% of these reactions, I'd say you're in a pretty good position, for you're studying for chapter 11. You understand most of what's going on in chapter 8, and that would be a good thing. All right. So there we go. Well, with that in mind, let's turn our attention to another question that's just as long, okay? This is question 11.2. The first two questions are really long. It says, identify the reagents that you would use to accomplish all of these transformations. If you're having trouble, take a look at the review of reactions. The review of reactions at the end of chapter 9. So this is the alkynes chapter. Try to do it yourself, and I see that my students are so fast that leads me to, a strong suspicion that you're not looking at the book. You're just like, I know it by now, just move on. Okay. Well, let's take a look at this one. So where should we start? I don't know. Let's start with this reaction right here. Okay. We're taking propine and we're converting it into 2-bromo-propene. So how would we do that? Well, this is a Markovnikov addition, isn't it? This is nothing more than a Markovnikov addition of HBr across the triple bond. However, I would point out that you're using one equivalent. Like I would literally write that down, just say one equivalent, because here now you're adding a second equivalent of HBr in a Markovnikov fashion again. Okay, and here I would write HBr again. I mean, here you could write XS would be fine, I think. Or you could just leave it as HBr like that. I don't think there's any problem with it, okay, the way that it's done. It's just that it's 2 Markovnikov additions. All right. And the next one is a reaction that we used many, many times. I remember in our chapter 9 practice, we did this, I remember like 3 times in a, at the end of a lecture one day, we were practicing and we said, okay, if we have a geminal dibromide like this here and we want to convert that into an alkyne, how do we do that? Well, we said it's a two-step process, right? First, you would treat it with excess sodium amide, and then you would treat it with water to add, not acid, you would treat it with water to add the terminal proton, right? Because you'd end up with the alkanide after the first step, but the water adds that last proton. And we said the same thing, right? These are geminal, those two bromines. Even if the bromines are vicinal, okay, we still use the exact same conditions. So I could literally take this and I can copy this and then paste it over here, okay? I'll just change the color to be cheeky. There we go. So either way is going to work. Okay, it's the same thing whether the the protons are geminal or vicinal. All right, there we go. Perfect. There we go. So where are we now? Let's go counterclockwise to make things interesting. All right. Does anybody have an idea about this reaction down here? Where you take, where's my pen? You take propine and you make acetic acid and carbon dioxide. Yes, absolutely. This is an ozonolysis reaction, isn't it? Right. And in the first step, you use water. Sorry, I got water on the brain here, I guess. The first step, you use ozone. The second step, you use water. Yeah, absolutely. Absolutely. All my students got it 100% correct, right? And this is an ozonolysis. And remember, whenever you have a terminal alkyne like this, you always end up with some CO2 gas being produced. All right. The next one is kind of a funny reaction. You're just taking propine and you're brominating the heck out of it, so to speak. So for that, I would just treat it with excess bromine. So literally just treat it with excess Br2, and that's just going to keep brominating until you get this tetrabromide here. Whereas the next one, we're just adding one molecule of bromine across the double bond. And so in that case, I would be careful to write Br2, but I would specifically write one equivalent. Okay. Now, if you look at our textbook, he doesn't write the one equivalent. He does write excess here. And either way is fine. Okay. As long as you understand that it's bromination, you're going to be able to figure it out. All right. The next one. It's kind of a long reaction arrow here, but we're going from propine to 2-butyne. So we're actually adding a carbon, right? And this is something that we did several times. We wanted to change the carbon skeleton. We want to add a methyl group. So that means that in the first step, we're going to treat it with, I wanted to use my red pen. We're going to treat it with sodium amide to do the deprotonation, right? That would give us this alkanide. And then in the second step, we're going to treat it with an electrophilic source of a methyl group. Absolutely, Kelly, 100%. So we're going to treat it with methyl iodide, just like that. Perfect. There we go. So that's a really powerful reaction, right? I told you that anytime you can change a carbon skeleton, it's a big deal in organic chemistry. Whenever you can do a change to a carbon skeleton, it's a big deal. All right, the next one, we're just going to keep going here. We're going to make this aldehyde, and we saw this reaction many times, that the only way that we have to make an aldehyde from an alkyne is to do an anti-Markovnikov addition of water, right? The first step is to treat it with 9-BBN or dicyamylborane, or if you just want to write R2BH, that works. And the second step is the oxidation like this. And of course, that doesn't produce an aldehyde immediately, right? It actually gives you this enol, which would be this enol. And that enol is going to undergo tautomerization to give you the aldehyde. And the next one, we're producing a methyl ketone. And so for this one, we need to do the Markovnikov addition across the triple bond. And I told you it's not that easy to do that, right? Because you end up making a vinylic carbocation, which is unstable. And so you have to spruce the reaction up. So we need to have sulfuric acid and water. But what's that special reagent we need? It's mercury 2 sulfate or mercuric sulfate. And what that would produce is this enol. I can draw it a little neater. There we go. We would end up with this enol, which would undergo tautomerization to give us the methyl ketone. All right. And then over here, we have all of our reductions. I didn't really give myself enough space here, did I? But hopefully you can see that this alkene is cis. This one is trans. And then the one in the middle is just hydrogenated completely. So for that, we would just use hydrogen and platinum. I'm going to go with the trans first. Does anybody remember the reaction conditions for the reduction to the trans alkene? Even part of it? If you just type in part of it, I'll know you know. I know you know. Yeah, absolutely. It's a sodium metal reduction, isn't it? Absolutely. Yes. Right. It's this. So this one's a sodium metal reduction. So you want to use sodium in liquid ammonia. Okay. Right. If you want to make the cis alkene, that's the one where you would use the poison catalyst. So hydrogen in Lindlar's catalyst. And again, I told you the way I remember that, and my students taught me this, is sodium. You write out the letter N like that for Na, and then you make a double bond, oops, like this, and you can see that it's trans, okay? Anyhow, there you go. I don't know if anybody used that, but my students come up with all kinds of mnemonics, which they love to share with me, usually in a lecture in person. And I'm sure that you've all developed strategies, right, for remembering reactions. Who's feeling more confident in their ability to remember these reactions? You know, um, who's feeling more confident than they did, let's say, I don't know, 2 weeks ago? He's like, you know what? I've looked at these enough by now, Mr. Dion, that I'm almost sick of them. I close my eyes at night and all I can see is a hydrogenation or a sodium metal reduction. Yeah, I think that's normal. It does take time to remember all these reactions, okay? Unless you have some kind of photographic memory or something like that, which I certainly don't have, it definitely takes practice. There's no doubt about it. And I think if you feel better about these two chapters, chapter 8 and chapter 9, that's a huge chunk, of what's really covered in this chapter. I mean, that's why it's the first two questions, because these are the kind of things that you have to have mastered to move forward. Now, the rest of the chapter, and I don't want to throw it under the bus, but the rest of the chapter is just kind of taking a look at all the different things that we learned over the course of the semester. And then we're going to try some practice problems here. So it says it's a good idea to review the two-step synthesis strategies from previous chapters. So let's say you wanted to remove a functional group around a molecule rather. We've got an alkyl halide here, but we've got a secondary alkyl bromide. We want to convert it into the tertiary, right? You can see that this is a Markovnikov addition here. No big surprise there. We just covered this. I mean, you would just use, you wouldn't use a highlighter. You would use HBr to do this, right? And you can see that this is the Zaitsev alkene. So to do that, you would use sodium ethoxide. And I don't think that would be a shocker to anybody, right? The only really tricky thing here, and I don't want to, what's the word, minimize the complexity of any of this, but the biggest consideration here, I think, as a student would be, what's my base? Well, I want to make a Zaitsev alkene, so I'm going to use a non-hindered base. The second step is Markovnikov addition. Students are usually pretty rock solid on that at this point, right? But if you were to make a mistake and choose potassium T-butoxide, what would that give you? That would give you the Hoffman alkene. Hoffman alkenes are cool, but that's not what you're looking at if you wanted to make this compound, right? And you can see that we could put the bromine over here, do a Hoffman elimination followed by an anti-Markovnikov addition. That's totally fine. But, really what I think the take-home message from this slide is, just besides the review of the reactions, it's look at the power that you have at this point. Don't take it for granted. You're able to take the bromine and put it basically almost wherever you want on the molecule. And that's a good thing to be able to do when you're trying to make new molecules. All right. I had an instructor when I was in my third year of university, and we asked him about some kind of molecule. We said, could you make this? And I remember without any hesitation, the guy was very confident, but he just looked at us and said, I can make anything. Anything in the lab you come up with, I can make it. If it can be made by human hands, I can make it. Anyhow, let's take a look at the next one. What if we have a hydroxyl? Right. We spent a good chunk of time talking about this at the end of chapter 7. We talked about all kinds of reactions with alcohols, right? And we said, well, an alcohol, just a hydroxyl is not a good leaving group, right? Because hydroxide is the conjugate base of water, which is not a strong acid. And so to convert it into a good leaving group, you have to treat it with tosyl chloride and pyridine. And what that gives you is the tosylate, right? So if I draw the tosylate that would be formed, which isn't drawn on here, it looks like this. And again, this is a good leaving group, right? Just like a iodide or a bromide or a chloride. So if we did an elimination on that with sodium methoxide, we would end up with the Zaitsev alkene. You can do a Markovnikov addition. What else could we do? We could take this and we could do an anti-Markovnikov addition to go back where we started. And here's an example of hydroboration oxidation, right? Taking this alkene, okay, and this, I said this is the reaction that we didn't look at thus far, right? Because if you were to treat this with aqueous acid, this alkene rather, okay, if you were to treat that with just aqueous acid, what would happen, right? You'd end up with this carbocation. I'll try to draw it as neatly as I can, right? And you'd end up with a hydride shift, wouldn't you? Okay, and so this is a specific example of needing to use oxymercuration, demercuration. So just something to think about there. All right. What else? You know, Hoffman alkenes, Zaitsev alkenes, and I think these are things that we're pretty good on, but you gotta always consider regioselectivity when you're choosing reagents, right? We need to know how to make a Hoffman alkene and how to make a Zaitsev alkene. Very important stuff. Well, let's see here. There's one more slide I just want to take a quick peek at, and that involves all these different hydrogenation conditions, right? And ways to take a double bond and convert it into a triple bond, right? We talked about doing a bromination, then double elimination, then adding water. So that's an important reaction. And then all these reductions, right? Lindlar's catalyst, sodium metal reduction, right? We talked about this a few minutes ago. This produces the cis alkene. This produces the trans alkene. Here, there's no cis or trans to worry about. All right. Anyhow, I think that's enough discussion on that. Let's try some practice. So this is question 11.3. Comes straight out of your textbook. I'm going to switch over to a blank document just because I like to not only provide the reagents, I like to write out all the intermediates. So just bear with me here, and we'll find a spot to do that. So let's go over here. So this is question what? 11.3. Question 11.3. Right out of your textbook. A. We're starting with an alkene. All right, and we want to convert it into the alkyne. And again, this is something that we've done many times. So what's the purpose here? Just to practice it, right? To make sure that we can pull up these reaction conditions out of our head and not have to think about it too much, right? Because we said the only way that we have to make an alkyne, if there's no change in the carbon skeleton, right? Because we have the same number of carbons. We have 4, 5, 6 carbons here, and then we have 6 carbons over here. Well, we're going to have to do a double elimination, right? So that means that we're going to have to start out with a bromide, right? A dibromide. And the easiest way to do that would be to do the bromination of the alkene, right? And again, if you're like, I'm not 100% sure what you're talking about, what I'm talking about is this, right? If we had the dibromide, where we have a bromine here and a bromine here, well, then all we have to do is the double elimination, right? Treat it with excess sodium amide followed by water. So how do we get from here to here? Well, that's just a bromination reaction, isn't it? So what are we going to do? We're going to take the starting material. We're going to treat it with bromine, Br2. We make the bromonium ion. The bromide comes in and attacks, and we end up with this compound. Okay, this is a stereocenter, but it's neither here nor there because we're going to do the double elimination in the next step. So first step is to treat it with excess sodium amide, which is a strong enough base to do that double elimination. Since you've got excess, then you end up with the alkanide, but then you throw water in and it protonates it, and there you go. So that's a 3-step synthesis. Okay, 3 steps, not too bad. Let's take a look at B. So this is one of those questions where we're moving a bromine around the molecule. So let's see if we can do it. We've got a primary alkyl bromide, and we're going to convert it into the tertiary alkyl bromide, you know. And this one, I just start, you know, it kind of screams retrosynthesis to me because, you know, what we need is we need to have this compound. We need to have the double bond here because then we can just do a Markov-Nikov addition of HBr across that double bond. So, now the question becomes, how do we make that alkene? Right? We have, if this is our alpha carbon, we've only got one beta proton, right? So what would be the best base to eliminate that, right? We don't want to use a non-hindered base because this is a primary alkyl halide, right? If we use something like sodium methoxide, that's a strong base, but it's also a good nucleophile. So that would mean that SN2 would predominate, right? If you go back to figure, the figure that we had in chapter 7, which is figure, I can't remember which one it is right now, if it's figure 7.2, anyhow, it's neither here nor there. But if we want the E2 to predominate, we're going to have to use a strong base, strong nucleophile. So the best choice here would be something like DBU or DBN. You could use potassium T-butoxide as well because it's a hindered base, but I'm going to use DBU. It doesn't get a lot of love in this class, so we'll use DBU, and that's going to give us this, and then we're just going to do a Markov-Nikov addition across that. So DBU, DBN, remember that these are strong bases, strong base, okay, but a weak nucleophile, a crappy nucleophile. All right, let's take a look at C. I think we did a question very similar to C earlier on this semester, but I think it's a good one. So we have this double bond here, and we want to make, so we're taking a Hoffman alkene and we want to convert it into a Zaitsev alkene. Does anybody have an idea where you might want to start on this? And this is a question where there's more than one solution for sure. Definitely more than one solution here. Does anybody have an idea? I see like 3 different ways that we could use. I'll take anything. I think probably my preferred way. Okay, somebody says HBr. Let's run with it. I like the way you think. Let's do that. We're going to throw in some HBr. Just going to do a Markov-Nikov addition. And there we go. So that would give us the bromine here. Perfect. And then if we want to do the elimination to make the Zaitsev alkene, what would we do? We're just going to treat it with sodium methoxide, right? Because this is a tertiary alkyl halide, we treat it with a strong nucleophile, strong base. The E2 is going to predominate. So there you go. Sodium methoxide. And if you want to choose sodium methoxide, that works too. I give this one 100%. There's nothing wrong with this at all. This is perfect. Okay. I'm going to show you another way that I think is kind of cool. Would be, let me just copy this. Take another crack at it. So this is perfect. It's a 2-step synthesis. Anytime you can do something in 2 steps, I say you've got a winner on your hands. So let's try this. So again, this is question 11.3. Just want to make sure I have it on the screen. So I think another cool way to do it would just be to do a Markov-Nikov addition of water across the double bond. You end up with the tertiary alcohol. And then one of my favorite reactions that I mentioned to you several times this semester is when you treat it with, just sulfuric acid and you crank the heat up, that's going to give you the thermodynamic alkene every time. Okay, so for this one, you'd only need one reagent. You just use sulfuric acid, and then you can make dilute sulfuric acid over here. Anyhow, so that would work. And I'd say there's even another way. It's not as elegant. Okay, it's not as beautiful. But if you did this, okay, it's kind of a goofy way of doing it, and I don't even know if this is in our textbook. But if you just hydrogenated this at the beginning to make 1-methyl cyclohexene, then you could treat it with bromine in light or heat, and that would give you the tertiary bromide, right? So that would take you right back here, and then you could treat it with sodium methoxide. It's an option. It's an extra step. And you might laugh at me and say, oh, the other ways are much faster. But hey, it would work, Again, not as elegant because it's 3 steps. But hey, who might have? I don't want to judge that harshly, right? So anyhow, we got 3 different ways really to make, the same compound. So that's kind of cool when you think about it. We'll put down here alternate, okay? Alternate, and this one is 3 steps. All right, give me 3 steps, right? Okay, and let's take a look at the last one in 11.3. So this is 11.3D. What is it? Oh, shoot. I didn't even realize that the same thing was in here. Sorry, I kind of already did the problem, didn't I? There we go. So for this one, your only option, look, if you're ever stuck on a question in Organic Chemistry 1 or Organic Chemistry 2 or any other organic chemistry class you would ever take, if you're starting with an alkane, you don't have many options, okay? You've really only got the option of halogenation. So you'd have to treat this with bromine and light. So I didn't realize that I just did this problem, okay? But anyhow, you end up with this, and then there you go. You would treat that with sodium methoxide, like that. There you go. All right. Now, something that all of these problems have in common is that none of them had a change to the carbon skeleton, right? We always started and ended up with the exact same number of carbons. And if you think about it, you know, we didn't learn that many ways to change a carbon skeleton. We got a few things for sure, but not a ton. So whenever you're posed with questions where it changes the number of carbons, you got to be able to recall all those reactions that we learned where you add or remove carbons. Most of the reactions that you have mastered this semester involved only functional group changes. So there's not as many options. And whenever you're limited, it's actually a good thing because, you know, you don't have as much to remember. So let's take a look here. Here's the good news, okay? So far, you've only learned one transformation that increases the number of carbons in a molecule. You've got one thing. That's it. In Organic Chemistry 2, you'll learn probably, you know, a dozen more things. But in this class, good news, you've only got one option if you want to increase the number of carbons, and that is to have an alkanide and use it as a nucleophile, and then to have a methyl or a primary alkyl halide and do an SN2. That's all you got. That's all we've got in this class. So you just do an SN2 like that, and there you go. That's the only thing that you've got in order to add carbons to a compound. So I like that. There we go. Now, in terms of decreasing the number of carbons in a molecule, we don't have much options, or we don't have many options there either. We've got ozonolysis, and based off of what I saw in question 11.1 and 11.2, my students have mastered, you know, ozonolysis. They get it. They say, okay, well, if I have a double bond that I want to cleave that, well, I'd use ozone followed by DMS, or the alternative, which is zinc and water. And if it was an alkyne, then I would use ozone followed by water. And it even says here at the bottom, it's like, yeah, in the future, meaning Organic Chemistry 2, you'll learn a whole bunch of reactions that change the carbon skeleton. But hey, this is Organic Chemistry 1. We spend a lot of time on things like acid bases, nomenclature. What else? Stereochemistry, right? Spectroscopy. We spend a lot of time on that stuff. So the focus of the class isn't just synthesis. This isn't just a synthesis class. But with all that in mind, let's try changing the carbon skeleton here. I bet you my students could solve this first one faster than me. You're starting it with acetylene, right? This is just plain old acetylene. That's the common name. The systematic name would be ethyne. And what are we doing? We're adding a methyl group on one side, and we're adding an ethyl group on the other side, right? Let me ask you a quick question. Does it matter the order in which I add these two alkyl groups? Does it matter if I add the ethyl or the methyl first? That's a yes or no proposition. Is this important? Should I pick one first? The answer is no, absolutely. Yes, it doesn't matter. I'm going to start with the methyl because it's on the left-hand side, and that's the way I read. So let's start with our acetylene, okay? Okay, first step, we're going to treat this with sodium amide. Then what are we going to do? We're going to treat it with methyl iodide, CH3I, okay? What's that going to give us? That's going to give us this compound. This is propyne. Next, we're going to treat it with another equivalent of sodium amide. So sodium amide, okay? What's that going to make? That's actually going to make this compound, right? Where you've got this alkanide, okay? that's going to be a good nucleophile. But what does your electrophile have to be? It's going to have to be ethyl iodide this time, right? Ethyl, let me write the whole thing here. So it's going to be ethyl iodide or ethyl bromide or ethyl chloride or technically ethyl tosylate. Really, you could use that. But that's just going to do an SN2 reaction like that. All right, nothing to it. I mean, it's not that there's nothing to it, but there you go. And there you have it, folks. You end up with this compound. Could anybody name this compound? And it's not me trying to trick you or anything. Could anybody provide a name for this compound in blue? Yeah, absolutely. It's 2-pentyne. Yes. Perfect. 2-pentyne. I like to practice my nomenclature as I move along. Yeah. So this compound here, this is benzyl bromide. Benzyl bromide. Benzyl bromide is oftentimes used as a electrophile in organic chemistry. Why? Because benzyl groups can be easily removed. And that's something that we learn in organic chemistry too. But benzyl bromide, I think I've told you this before, is one of the most powerful lacrimators there is. Like if you drop one drop or a half a drop, it'll make everybody in the room start to sob and cry. You know, it makes your eyes water really, really badly. Okay, well, this one is kind of an interesting one because we're adding the 2 carbons of the triple bond. And in order to do that, you would just need acetylide as a nucleophile, right? As long as you had the acetylide ion, which comes from sodium acetylide, it could just do the SN2 and you're done. So where do you get the acetylide ion from? You know, this is where you have to kind of say, well, I would have a small compound like acetylene in my disposal. So we would start with acetylene, and we would treat that with sodium amide. That would give us the acetylide ion, and then you would treat that with your benzyl bromide. So just this compound here, and that is going to give you the product. Okay, and we can shorten that to this. There you go. So remember, in organic chemistry, you can always assume that you have little molecules like ethyl iodide, acetylene. Usually we take artistic license with that stuff to some degree. You can just assume if it's a small molecule that you've got it. So, you know, if you're still struggling at this point and, you know, you're looking at a problem, you're saying, well, what do I do? You know, how am I going to approach a synthesis problem? It says to approach any synthesis problem, answer these first 2 questions. So, is there a change in the carbon skeleton? Is it gaining or losing carbons, right? And then if it's gaining carbons, well, you've got to use an acetylide or an alkanide ion, do an SN2. If it's losing carbons, again, something like ozonolysis. And then is there a change in identity and location of functional groups? So for that, it's more like your chapter 7 chemistry, where you have to do Hoffman and Zaitsev elimination and stuff like that. But again, and I'm kind of repeating myself, I sound like a broken record here, but in order to solve a synthesis problem, okay, you've got to be able to recall all of the reactions that we've learned, and you've got to work through many, many examples. Well, the fact that it's on a slide proves that if you're like, well, I have to practice a lot. Well, it's not just you. It's everybody who has ever taken this class and everybody who ever will and everybody who teaches it too, okay, has to practice a lot. Let's take a look at a couple of problems here kind of quickly. If you had a problem like this one here, how many carbons are we starting out with? 1, 2, 3, 4, 5. So 1, 2, 3, 4. We've got 5 carbons in our starting material, and we're ending up with 7 carbons, right? You see that we have the triple bond on the end here, but we've got a double bond here. So that means we're adding these 2 carbons. So how would we do that? We would treat the molecule with sodium amide followed by ethyl iodide, right? So we would treat the molecule first with sodium amide to deprotonate. Then we would treat it with ethyl iodide, okay? And that would give us this intermediate. We would have the triple bond rather, and then the ethyl group here. And then to reduce that to the transalkene, what do we use? Just plain old sodium metal reduction, like that. Sodium in liquid ammonia. So not much of a stretch there. I'm sure that most people would be able to get that kind of synthesis pretty quickly, okay? There we go. So, you know, how did we do that? Well, we had to know about adding the 2 carbons. So we had to know about deprotonation and using the alkanide as a nucleophile, right? And then we had to know, well, you've got to add 2 carbons. So you've got to be able to count carbons correctly. And then you had to know the reduction to a trans alkene, right? All stuff that we've covered several times, okay? Remember that you've got to have your numbers here, and obviously when we're doing the class remotely, you know, most of our quizzes are multiple choice, so you don't have to stress about the number of steps, maybe in the homework a little bit more, but something you want to remember when you're stepping into organic chemistry too, and I know that many of you are interested in taking that class in the next few months, you know, the numbering is really important. You know, you could master all these reactions, but if you just were to try to mix sodium amide, ethyl iodide, and sodium, that would probably be dangerous for one thing, and it would not give you anything. It would just make a mess. So the numbering is extremely important in organic chemistry. All right, here we go. So we've made it all the way to question 11.7, which is identify reagents that could be used to achieve each of the following transformations. And you can clearly see just by taking a very quick glance at these questions. So this is 11.7a, this is D, and this is E. You can see there's changes to the carbon skeleton in all of these problems, aren't there? All right, well, I'm going to switch over to a blank document just so that I have enough room here. And we're going to tackle these. I'm going to give them the old college try. We're going to do it for Clyde. All right, Clyde is the school's mascot. So let's give it a shot here. So we've got 1 pentyne. There we go. And there we go. And we're trying to make this molecule. So we've got 1 pentyne. So we've got 5 carbons in the molecule. And here we have 1, 2, 3, 4, 5, 6, 7, 8. So we've got cis 4-octene. So let's write that down. So we're going to do cis 4-octene. All right. There we go. Or you could call it Z4-octene. Either way would be perfectly fine. All right. So let's see here. 1 pentyne and cis 4-octene. So we're adding a total of 3 carbons to the molecule like this. So what are we going to do to add 3 carbons? Well, we know that the only way we can add carbons to this is to deprotonate. So let's treat this with sodium amide, and I'm going to break it down step by step here. That would give us this alkanide ion, wouldn't it? Okay. So if we have this alkanide ion and we treat this with propyl iodide, so, or you could use propyl bromide, whatever, propyl chloride, that's going to do an SN2 reaction where we lose the iodide as the leaving group, and we would end up with this. There we go. 1, 2, 3. So we've added the carbons, and then all we have to do is reduce it to the cis alkene. So we're going to use hydrogenation, Lindlar's catalyst. All right. Next, we've got 11.7D. Take a look. 11.7. This is D. We're starting out with this alkene. Didn't we see this alkene already today? I think we did. So, and then we want to make this compound. All right. So if we count here, like 1, 2, 3, 4, because the gem dimethyl is not going away. And if we count here 1, 2, 3, 4, then you've got 5, 6, 7. So we're adding a total of 3 carbons here. Okay, so how would we do this? Because we've got a double bond, and we can't do just bromination, right? Because if you were to do a bromination, let me show you something that would be wrong, okay? If you were to just do a bromination here, okay, and then you did the double elimination followed by addition of water to make this compound, okay, if you just have the triple bond, which I can draw more neatly than that, if you just had the alkyne, that's not going to get you in the right place, because yeah, you can add 3 carbons to that, but then you'd have 1, 2, 3, and your functional group, your alkyne, is in the wrong spot, right? You'd need it to be over here. So this would not work. This would be an inappropriate strategy, right? But I have another idea. I think we need to do 2 different steps to add the carbons to the molecule, because if we did this, right, I'm going to do my retrosynthesis like this. If we had this compound, so I just want to make sure I got my carbons right here. So we have 1, 2, 3, 4, 5, 6. If we had this alkyne, then all we'd have to do is add methyl to it and then do the reduction to make the trans alkene. So then I think the question becomes, well, how would we go from here to here? Because then all you would be doing would be adding these two carbons. Right, well, how do you add those two carbons? You could add them from acetylide, which is a good nucleophile. And so how would we do that? Well, let's see. If we were to take the starting material, and if we did an anti-Markovnikov addition of HBr across the double bond, then we end up with a primary alkyl halide like this, and that's a powerful electrophile. So then you can always assume that you have sodium acetylide, so just this acetylide ion, okay, which is a very strong base, but it's also a wicked nucleophile, and you've got a primary alkyl halide. So that's going to do an SN2 reaction like this, okay, like that. So now we're going to have our triple bond here. Son of a gun. I find triple bonds are hard to draw on the iPad. Come on. There we go. I always have to twist it. Okay, there we go. Now we can add our methyl group, can't we? Because all we'd have to do is treat this with sodium amide as our base to make the alkanide. And then in the second step, we would treat that with iodomethane or methyl iodide, same thing. And that would give us this compound. There we go. And now we have, let me make sure, 1, 2, 3. No, I've added too many carbons. What did I do here? 2. I added an extra carbon here, didn't I? Oops. So let's see, let's try it again. No. Here we go. And so now we're going to add our methyl group. So we're going to use, or no, we already did that, so I just didn't put it on here. And then to reduce to the transalkene, we're going to treat that with sodium and liquid ammonia, like that. There you have it. So let's try one more. So this is 11.7E. 11.7E. So we're going to start with this tri-substituted alkene, and we want to make this compound where we have a terminal alkyne. So we're starting out with 5 carbons in the first molecule, then we have 1, 2, 3, 4, 5, 6, 7. So we're adding 7 carbons, right? And if we have the triple bond over here, right, in terms of our retrosynthesis, the best way to do that would be to have this compound, right, and then to use sodium acetylide as a nucleophile, right, going this way. Okay, and then we just do an SN2 and we're done. So then the question is simplified, and how do we get from here to here, right? We just have to move that bromine, or put a bromine on there, we have to move it around the molecule. So the first thing we're going to do, should we start with a Markovnikov addition of bromine, or HBr rather, or an anti-Markovnikov? Could anybody make a suggestion? Would my first step to be HBr or HBr and peroxide? So peroxides, what am I doing here? Would I start with a Markovnikov or anti-Markovnikov addition? Yeah, you'd want to start with an anti-Markovnikov addition of HBr across the double bond. So you'd end up with this, okay, like this. Then in order to get to this compound, right, we'd have to think, well, you know, we would need to have this, and then we'd have to do another anti-Markovnikov addition, wouldn't we? So let's do that. So for that, we would need to use a hindered base like potassium T-butoxide. That's going to give us the Hoffman alkene. Then we can treat that with HBr. Oops. HBr and peroxides again to do the anti-Markovnikov addition, like that. And then we would treat it with sodium acetylide, which you can just write like this. Sodium acetylide. Oh, it's probably all deleted now, isn't it? No, it's not. Son of a gun. Miracles never cease. There you go. All right.